Okay, now we're going to discuss the state space model of the same simple circuit with the given values of 5 ohms, 3 farads, 3 ohms, and 2 henries. To solve, we first identify the state variables. In identifying the state variables, where we have the option of choosing among the different unknown values of the circuit. Basically, and for simplicity of discussion, let us choose the charge across the capacitor and the IT, now the current within the circuit are, as our state variables. So, as I have mentioned before, there are many variables in this circuit, no? Not just the QT and the ID. It's also the voltage drop across this resistor, this capacitor, voltage drop at the capacitor, voltage drop at this resistor again, and voltage drop in this um, inductor. They are also variables, and of course the current, no, within this circuit is also a variable, and of course the charge, no, in this capacitor. Okay, and there are many variables. Now, you are to choose what will be your state variables. But of course, the hint here is you choose a state variable that will lead you to your unknown values, to what you are supposed to derive. Okay, now in this case, and just like in your laboratory activities per group. Okay, so I allowed you to use the Q of t and I of t as state variables. Okay, but let me reiterate that aside from the two, you may use other state variables from among the different unknown values of the circuit. Now, if you're going to continue, Uh, the next is to identify the state equations. Now, what are state equations? So, state equations are equations of the uh, state variables, no? Because since you have your qt and it as your variables, then you need to derive state equations for them. State equations that are the first derivative of this state variable. So meaning to say, the equation of di dt and dq dt are will be the state equations. So once more by KVL from our given circuit, and these are the voltage current relationship, no, among the components based on table 2.6, now if you remember from our PowerPoint presentation from the transfer function. Okay, so the voltage, the KVL is uh, given by VI is equals to voltage drops at the resistor 5 times IT, voltage drop across the inductor, no, the 1 over 3 IDT plus in the resistor again 3I, and for the inductor 2 DIDT. So once more saan natin na ito nakuha based sa table 2.6, no? Okay, now from here we combine the 5IT and 3IT, so we have 8IT here, and the integral of IDT is equivalent to QT, and then we copy this. Since we need to know the equation of dIdt, so we simply transpose like this one. So dIdt is equal to negative 1 over 3 qt, negative 8 over t, plus vit. And transposing the numeric coefficient 2 on the other side, therefore we have dIdt to be equal to 1 over 6 qt minus 4 it plus 1 half vit. So Please note also that we have already defined, no, in our PowerPoint presentation that dq over dt is equivalent to I of t. And since dq dt is the first derivative of qt, which is our state variable, therefore, the dq over dt is another state equations that we are finding. And so dq dt could also be written as 0 qt plus 1 it plus 0 vi vt. So these two, the equation of dq dt and the equation of di dt, are the state equations. And once more, the state variables are qt and it. Okay? So the derivative of these state variables will be the state equations. Next is if we need to solve, no, the simultaneous equation of our state variable, since we have two variables in this case, the qt and the it, no, those are the two variables. Take note, vit here is not considered as a variable, but that is an input signal. No? That would be, yes, of course, it's a variable, but that is a known, no, known variable, okay, depending on the input signal that you're going to apply to it. So the variables here are the qt and the it. So to put our equations in standard form of the state space model, let's use some notations. No? So let's let x sub 1 equals to qt and let x sub 2 equals to it. And therefore, since the derivative of qt is dq dt, then by symbol, let's assign the derivative of x sub 1 is x sub 1 dot, and the derivative of x sub 2 is x sub 2 dot. And let us use the notation u to be our input variable vit, and let us use the symbol y to be our output variable vl of t. Okay, and if we're going to rewrite our state equations in terms of this standard notations of x's, no, and y's, then our x sub 1 dot, which is dq dt, rather x sub 1 dot, which is equals to dq dt, will be equal to this equation. No? Okay, so it will be 0 qt or 0 x1 plus 1 x2 plus 0 u. Okay, we just simply converted, no, the variables into a notation. Okay, and for x sub 2 dot, no, that's the equation of di dt. No, x sub 2 dot is equal to di dt as we have assigned. And then, so therefore, x sub 2 dot will be 1 over 6 x1 minus 4 x2 plus 1 half u. Okay? And for the output equation, okay, our y is equals to VL of t. Okay? And so this VL of t, take note, is the voltage now across this inductor, uh, where there where we get our output voltage, no, across the inductor. So once more, from this equation, no, of our KVL, okay, take note that this V sub L is equals to 2 di dt, which if we're going to transpose this on the other side, so our VL will be equal to negative 1/3 QT negative 8 I of t plus VIT. And so therefore, by So this is our output equation. 1/3 x1 means it x2 plus u. So once more, these are the state equations, and this is the output equation. So if we're going to write it in vector matrix form, it would be like this, no? The state variables x1 dot x2 dot will be equal to the matrix A. So this is the matrix A, 0, 1, -1 over 6, -4. Okay, those are the coefficients of this. Okay, and x1, x2 here plus 0 and 1/2. These are the coefficient of this u. Okay, and for the y, the coefficient -1/3 and -8, x1, x2 plus the u. Okay, so this is how we write, no, the vector matrix form. And please note that uh, the standard the standard form of our state space, once more, that will be equals to x1 dot x2 dot equal to matrix A, and then the x1, x2 plus the matrix B times the u. And then for the y, that is equal to matrix C, x1, x2 plus matrix D times the u. Okay, please make sure, no, that you're familiar with this standard notation of writing the vector matrix form of our state space model.